At first glance, Neptune does not look like a nightmare. It looks calm. It looks distant. It looks like a perfect blue marble suspended in the silent outer darkness of the solar system. From Earth, it does not blaze like Venus. It does not dominate the night like Jupiter, and it does not wear the golden rings that make Saturn instantly recognizable. Most people could go their entire lives without ever seeing Neptune with their own eyes, because it is too faint to be seen without a telescope. It sits so far away that even sunlight feels weakened by the time it arrives there, softened into something closer to twilight than the warm daylight we know on Earth. But that quiet blue face is almost a disguise, because Neptune is not peaceful. It is an ice giant wrapped in supersonic winds, storms large enough to swallow Earth, strange dark vortices that appear and vanish, a tilted magnetic field that behaves like something broken, rings that should not stay clumped the way they do, and a captured moon so cold and strange that it still erupts geysers into space. Neptune is not just the farthest major planet from the Sun. It is one of the most mysterious places in the entire solar system. And the more you learn about it, the less it feels like a calm, blue world. It begins to feel like a warning. Before we begin, if you enjoy calm space documentaries like this, take a moment to subscribe to the channel, leave a like, and write a comment telling us where you are watching from and what time it is for you right now. It is always fascinating to imagine people around the world, in different countries and different time zones, looking up at the same universe together. Tonight, you are watching the Just About Space channel, talking about why Neptune is more terrifying than you think. Now, let's drift outward, past Earth, past Mars, past the giant worlds, and into the deep blue darkness where Neptune waits. To understand why Neptune is so unsettling, we first have to understand how far away it really is. Distances in the solar system are easy to say, but almost impossible to feel. We say Earth is about 93 million miles from the Sun, and that already sounds enormous. Light, the fastest thing in the universe, takes about 8 minutes to cross that distance. When sunlight warms your face, that light left the surface of the Sun 8 minutes earlier. But Neptune is not 8 light minutes away from the Sun. Neptune is roughly 30 times farther from the Sun than Earth is. On average, it orbits at a distance of about 2.8 billion miles, or about 4.5 billion kilometers. Sunlight needs more than 4 hours to reach it. Imagine that for a moment. If the Sun suddenly vanished, Earth would continue orbiting normally for 8 minutes before anything changed. Neptune would remain unaware for more than 4 hours. Its day would continue. Its clouds would move. Its winds would scream around the planet. Its moons would keep circling. And only hours later would the darkness arrive. That distance changes everything. Sunlight at Neptune is not the bright, life-giving force we know. NASA describes high noon on Neptune as looking like dim twilight to us. The sunlight Earth receives is roughly 900 times brighter than the sunlight at Neptune. That means the Sun is still the brightest object in Neptune's sky, but it no longer feels like the center of a warm planetary system. It is more like a brilliant star that happens to rule from an almost impossible distance. And that is part of the terror of Neptune. It is not terrifying because it is fiery. It is terrifying because it is remote. It belongs to a part of the solar system where the Sun is no longer a comforting presence. There is light there, but barely. There is energy there, but not much. There is movement, weather, storms, and violence, but all of it happens in a region that should almost feel frozen into stillness. Neptune is so far out that a single orbit around the Sun takes about 165 Earth years. Since its discovery in 1846, Neptune has completed only one full orbit. A person born on Neptune, if such a thing were possible, would not see a single Neptunian year end during a normal human lifetime. Seasons there are not measured in months. They are measured in decades. Because Neptune's axis is tilted, it does have seasons, but each one can last more than 40 Earth years. Think about what that means for a world of storms. On Earth, seasons shift quickly enough for us to feel the rhythm of the planet. Spring, summer, autumn, winter. Weather patterns change. Temperatures rise and fall. Life responds. But on Neptune, the seasons crawl. A single hemisphere can spend decades leaning slightly more toward the sun, not enough to make it warm, but enough to reshape chemistry, cloud formation, and atmospheric patterns over timescales longer than civilizations remember weather records. If Earth weather feels unpredictable after a week, imagine trying to understand a planet where one season lasts longer than most human careers. This is not a place built for human intuition. It is a place where time, distance, light, and weather all operate on scales that feel wrong to us. Neptune is the same solar system we live in, but it feels like a different category of world entirely. There is also something psychologically strange about Neptune's color. Blue is the color we associate with water, sky, calm, and distance. On Earth, blue is comforting. It is the ocean on a clear day, the sky after a storm, the quiet background of life. Neptune borrows that emotional language and then betrays it. Its blue is not an invitation, it is chemistry. Methane in its atmosphere absorbs red wavelengths and helps leave blue light behind. The color is not a promise of oceans, breathability, or peace. It is a spectral effect in a hydrogen-helium atmosphere over layers no human could survive. This matters because humans are visual creatures. We judge danger quickly by appearance. A red lava planet looks hostile. A gray asteroid looks barren. A yellow sulfur world looks poisonous. But a blue planet activates the part of our imagination that thinks of Earth. Neptune tricks that instinct. It reminds us that the universe can use familiar colors for completely unfamiliar reasons. Blue does not mean safe. Beautiful does not mean gentle. Familiar does not mean habitable. If anything, Neptune's beauty makes the danger sharper. It is a world you want to look at, but never approach. A world that feels almost peaceful until you understand that beneath the soft color are winds no building could endure, depths no probe could easily survive, and pressures that erase the idea of a surface. The planet is a lesson in not trusting cosmic appearances. Neptune is also unsettling because, for most of human history, it was completely invisible. Mercury, Venus, Mars, Jupiter, and Saturn were known in ancient times because they can be seen with the naked eye. They wander across the sky, bright enough for early civilizations to notice and name. Uranus can barely be seen under very dark skies, though it was not recognized as a planet until the telescope age. But Neptune is different. It is too faint for ordinary human eyes. It was not discovered because someone simply looked up and saw it. It was discovered because mathematics said something had to be there. That alone gives Neptune a strange feeling. It was not found first as a light in the sky, but as a gravitational whisper. Astronomers noticed that Uranus was not moving exactly as expected. Its orbit seemed slightly disturbed. Something unseen appeared to be pulling on it. The invisible planet was predicted before it was confirmed. In 1846, Johann Galle observed Neptune near the predicted position, turning an equation into a world. Neptune became the first major planet discovered through mathematical prediction rather than direct naked-eye observation. There is something beautiful about that, but also something eerie. It means Neptune announced itself through its effects, not its face. It was a hidden presence at the edge of the known solar system, tugging faintly on another planet from the darkness. Before anyone clearly saw it, Neptune was already there, shaping the motion of worlds. That is one reason it feels different from the familiar planets. It was not part of humanity's ancient sky. It was a secret we had to calculate. And after we discovered it, Neptune remained mysterious for a very long time. Even through telescopes, it was mostly a tiny blue disk. We could measure its orbit. We could estimate its size. We could see that it was distant and cold. But we could not truly see its weather, its storms, its rings, or the bizarre activity on its largest moon. For more than a century, Neptune was a planet known more by numbers than by experience. It existed in textbooks as a far blue dot, a boundary marker, the last major planet before the Kuiper Belt and the deeper outskirts of the solar system. Then Voyager 2 arrived in 1989, and suddenly Neptune stopped being an abstract blue dot. It became a world. Voyager revealed clouds, storms, rings, moons, and strange active geology around Neptune's system. It showed that this remote planet was not quiet. It was dynamic. It was violent. It was full of motion. And in a way, that made Neptune more disturbing. Because before Voyager, we could imagine the distant ice giant as a frozen, sleepy world. After Voyager, we had to face the fact that the edge of the planetary solar system was alive with storms. But Voyager was also a reminder of how little we know. No spacecraft has visited Neptune since. Every close-up view we have of this planet came from one fast flyby in 1989. That means nearly everything we say about Neptune still carries a shadow of uncertainty. We have watched it from Earth and from space telescopes, but we have never placed an orbiter there. We have never sent a probe down into its atmosphere. We have never watched its storms from close range for years. Neptune is one of the major planets, and yet it remains one of the least explored. That is part of its power as a story. It is not only dangerous because of what we know, it is dangerous because of how much we still do not. Neptune's distance also changes how we think about information itself. When a telescope observes Neptune, it is seeing light that has traveled for hours across the solar system. When a spacecraft sends data back from Neptune, the signal is faint, delayed, and stretched thin across billions of miles. The information arrives slowly, carried by radio waves that must be captured by giant antennas on Earth. Every bit is precious. Every image from Voyager 2 had to cross an ocean of darkness before becoming something humans could see. That gives Neptune's data a different emotional weight. A photo of Mars can feel immediate because Mars is relatively close and constantly explored. A photo from Neptune feels like a message in a bottle from the edge of the planetary system. It is not merely an image. It is proof that a machine survived long enough to look back from a place almost beyond ordinary imagination. This is why the Voyager-Neptune encounter still feels historic. It was not just science. It was a fragile line of communication stretched across the solar system. On one end, a small spacecraft passed a giant blue planet. On the other, humans waited on Earth for the data to arrive. That delay, that distance, and that dependence on technology make Neptune feel like a place at the edge of reach. If you could somehow travel toward Neptune, the first thing that would happen is that the solar system would begin to feel emptier. At first, leaving Earth, space still feels connected to home. You pass the moon, and the Earth remains a large, bright world behind you. You pass Mars, and the sun still looks powerful. You pass the asteroid belt, and Jupiter grows enormous ahead. Even at Saturn, the sun is still clearly the ruler of the system. It is smaller, but it still has presence. Its light still shapes the rings. Its gravity still feels obvious in the architecture of the planets. But as you continue outward, something changes. The sun shrinks. Not because it becomes weaker in reality, but because distance turns even a star into a point. At Neptune, the sun would look like an intensely bright star, but not like the golden disk we know from Earth. It would be too small to warm the world in any ordinary sense. It would not rise into a sky full of blue air. It would hang in the blackness, sharp and far away, pouring only a faint fraction of the energy Earth receives. This weak sunlight is important because it makes Neptune's atmosphere more mysterious. On Earth, the sun drives almost everything in the weather system. Sunlight warms the surface. Warm air rises. Winds move. Water evaporates. Clouds form. Storms grow. Our atmosphere is powered by solar energy interacting with land, ocean, and air. Jupiter and Saturn receive less sunlight than Earth, but they also have powerful internal heat and huge atmospheres that maintain motion. Neptune receives far less sunlight than any of them, and yet it has some of the fastest winds in the solar system. That is what makes Neptune so strange. It should be slow. It should be calm. At least, if you imagined weather as something simply powered by sunlight, Neptune should be one of the quietest giant planets. But it is not. Its atmosphere is swept by winds that can reach more than 1,200 miles per hour, or about 2,000 kilometers per hour. That is faster than the speed of sound in Earth's atmosphere at sea level, though sound speed depends on temperature and composition. These are not gentle breezes on a faraway frozen planet. These are winds so fast they make Earth's strongest hurricanes seem small. And those winds are happening in near darkness. That is the unsettling part. Neptune is like a machine running in the cold, far from the obvious power source. A planet so distant that noon looks like twilight, yet its atmosphere races faster than almost anything we know. This makes the world feel alive in a way that should not be possible. It is not alive, of course. It is physics. It is heat, rotation, chemistry, turbulence, and fluid motion. But from a human perspective, it feels almost unnatural. The cold does not make Neptune still. The darkness does not make Neptune quiet. Instead, something inside the planet helps keep it restless. Neptune emits more heat than it receives from the sun. It radiates internal energy into space, a leftover and ongoing source of warmth from formation, compression, and deep planetary processes. That internal heat may help drive weather from below, creating convection, storms, and powerful winds in an atmosphere far removed from the sun. So Neptune is not simply a cold ball at the edge of the solar system. It is a dark blue engine. And we do not fully understand why that engine behaves the way it does. Another terrifying detail is Neptune's lack of a human-friendly scale. On Earth, even enormous things can be compared with the body. A mountain is huge, but you can climb it. An ocean is vast, but you can cross it. A storm is frightening, but you can understand its size on a map. Neptune's features are planetary in a way that breaks ordinary comparison. A storm can be as large as Earth. A wind band can wrap around the planet. A season can last longer than a human generation. A pressure layer can extend deeper than entire rocky worlds are wide. This scale mismatch makes Neptune hard to emotionally process. We can say the Great Dark Spot was Earth-sized, but that sentence is almost too large to feel. Earth is everything we know. Every city, forest, ocean, person, animal, mountain, and memory. To say a storm can be comparable to Earth is to say Neptune's weather can contain our world as a unit of measurement. That is not just science. That is a kind of cosmic humiliation. And yet Neptune itself is not even the largest planet. Jupiter is much bigger. Saturn is more massive than Neptune. This means the solar system contains multiple worlds whose ordinary atmospheric structures can dwarf human civilization completely. Neptune is terrifying partly because it reminds us that nature does not reserve its grandest scales for rare cosmic events. Sometimes a storm on a planet is already enough to make Earth feel small. One of the most terrifying truths about Neptune is that you could never stand on it. This sounds obvious when we remember that Neptune is a giant planet, but it is worth slowing down and really imagining it. Many people picture planets as worlds with surfaces. Earth has a surface. Mars has a surface. The Moon has a surface. Even Venus and Mercury, hostile as they are, have ground. You could not survive there unprotected, but there is a place where your feet could touch something solid. Neptune does not offer that kind of world. It is not a rocky planet wrapped in gas. It is an ice giant, a massive world made mostly of hydrogen, helium, methane, and deeper materials that scientists call ices, not because they are necessarily frozen like ice cubes, but because they are substances such as water, ammonia, and methane that were considered volatile in the early solar system. Under Neptune's extreme pressure and temperature, these materials do not behave the way they do on Earth. They become dense, hot, strange fluids. The planet's atmosphere gradually merges into deeper layers until the distinction between sky and interior becomes meaningless. If you fell into Neptune, you would not hit a surface. You would descend. At first, you would pass through the upper atmosphere, where methane absorbs red light and helps give Neptune its blue appearance. You would fall through layers of cloud and haze. The pressure would rise. The temperature would change. The sunlight would fade above you. There would be no horizon like an ocean or land, only atmosphere thickening around you, squeezing harder and harder. Eventually, the pressure would become crushing. Far below the visible clouds, the gases would become denser, then fluid-like. Water, ammonia, and methane under extreme conditions might form a deep mantle of hot, dense material. Scientists even think there may be an ocean of superhot water beneath Neptune's cold clouds, prevented from boiling by the immense pressure above it. That phrase sounds contradictory, but it is exactly the kind of contradiction Neptune creates. A planet that is freezing at the top, yet may contain hot exotic fluids deep inside. This is not an ocean like Earth's ocean. It is not a sea you could float on. It would be buried beneath crushing layers at pressures far beyond anything human technology can easily survive. The chemistry would be extreme. The boundary between liquid, gas, and other phases might blur. If there is a rocky core at the center, it is hidden under enormous amounts of material, unreachable and unimaginable by human standards. This is why Neptune is terrifying as a place. It is not simply that it would kill you. Many planets would kill you. Venus would crush and cook you. Mars would freeze and suffocate you. Jupiter would tear spacecraft apart with radiation and pressure. But Neptune is terrifying because it has no human scale at all. It is all atmosphere, pressure, depth, and darkness. There is no mountain to land near, no plain to cross, no visible ground where a rover could drive. It is a planet made of descent, a world where every meter downward becomes worse. The deeper you fall, the less Neptune resembles a planet in the way your mind understands planets. It becomes a pressure machine, a blue abyss, a place where the sky never ends. It just becomes heavier. There is a quiet horror in the fact that Neptune's most violent motions are almost invisible from Earth. If a hurricane forms on Earth, satellites watch it, news reports track it, people evacuate. We name the storm because it affects us. On Neptune, storms can form larger than continents, larger than Earth, and no living creature there notices. There is no ocean surface feeling the wind, no forests bending, no cities preparing, no animal instinct sensing pressure changes. There is motion without witness, weather without life, violence without consequence except the physics of the planet itself. This is a recurring theme in astronomy. The universe is full of events that would be overwhelming if they happened near us, but they occur in places where no one is present. Stars explode in galaxies far away. Black holes feed in silence across cosmic distance. Worlds freeze, melt, collide, and drift without observers. Neptune's storms are part of that same reality. They are enormous but detached from human drama. And maybe that is why they feel so strange. We are used to danger, meaning danger to someone. Neptune's danger exists even without victims. It is not evil. It is not trying to harm anything. It is simply powerful. That indifference is one of the deepest sources of cosmic fear. The winds of Neptune are one of the clearest reasons the planet deserves fear. On Earth, wind is familiar. It can be gentle, comforting, even beautiful. A breeze through trees, a storm against a window. But wind is also one of nature's most violent forces. Hurricanes tear apart buildings. Tornadoes lift vehicles and destroy entire neighborhoods. Jet streams shape weather across continents. And yet, the most powerful winds on Earth are almost nothing compared to Neptune. Neptune's winds can move faster than 1,200 miles per hour. That is more than 2,000 kilometers per hour. At those speeds, clouds of frozen methane are whipped around the planet with unbelievable force. If a human-made aircraft could somehow exist in such an atmosphere, it would not be flying through weather. It would be inside a planetary-scale blast. But the real terror is not only the speed. It is that these winds occur on a planet receiving almost no sunlight compared with Earth. That makes them feel wrong. At Neptune's distance, there should not be enough solar energy to drive such violent atmospheric motion in the simple way sunlight drives weather on Earth. Yet Neptune is the windiest world in the solar system. This tells us that the atmosphere is not merely responding to the sun, it is responding to Neptune itself. Internal heat, rapid rotation, deep atmospheric layers, and complex chemistry all contribute to a weather system that remains active in the dark. Neptune rotates once every roughly 16 hours. That is fast for such a large planet. Rapid rotation helps organize atmospheric motion into bands and jets. On giant planets, rotation matters enormously. It shapes storms, bends winds, and creates large-scale patterns through the Coriolis effect. But Neptune's patterns are not as neatly familiar as Jupiter's belts and zones. They are more hidden, more subtle, more changing. Bright methane ice clouds appear and move. Dark storms form and vanish. The planet's face can shift dramatically over time. When Voyager 2 flew by Neptune, it saw bright clouds racing through the atmosphere and a huge dark storm called the Great Dark Spot. This was not a little blemish. It was an enormous oval system, large enough in its longer dimension to span the size of Earth. Imagine looking at a planet and seeing a storm the size of your entire world. On Jupiter, the Great Red Spot has lasted for centuries. But Neptune is different. When Hubble looked again in the 1990s, the Great Dark Spot had disappeared. That is unnerving. A storm large enough to hold Earth appeared in the data, became one of the defining images of Neptune, and then vanished within years. Later, Hubble saw new, dark storms on different parts of the planet. Neptune's storms are not permanent monuments. They are enormous atmospheric events that can be born, drift, distort, and die. They make the planet feel less like a static object and more like a living weather system whose largest features can change between generations of observation. And because Neptune is so far away, we cannot watch it with the intimacy we watch Earth's weather. We cannot place satellites in orbit around it, at least not yet. We cannot release weather balloons into it. We cannot track every storm from above. We study it through powerful telescopes and one historic flyby. That means Neptune's atmosphere still contains deep unknowns. We can model it, observe it, and compare it with other planets, but we are still trying to understand how its winds become so extreme. So when you look at Neptune's smooth blue face, remember what that color is hiding. It is hiding a world where the wind can move faster than bullets, where Earth-sized storms can form and disappear, and where darkness somehow powers motion instead of silence. Neptune also forces us to think about the future of the sun's influence. Right now, Neptune is barely warmed by sunlight, but it is still gravitationally tied to the sun. In the far future, as the sun evolves into a red giant, the outer solar system will change. The inner planets may be scorched or engulfed, while the distant regions receive more warmth than they do today. Worlds now frozen may briefly experience very different conditions. The balance of heat, ice, and chemistry across the solar system will shift. Neptune itself will not become Earth-like. It is too massive, too gaseous, too alien. But the idea that even the outer planets will experience the sun's aging reminds us that no world is permanent in its current state. Neptune feels timeless because its year is so long and its distance is so great, but it too belongs to a changing star system. Its atmosphere, moons, rings, and orbit exist inside a cosmic clock. This adds another layer to its story. Neptune is not just the final major planet of the present solar system. It is also a witness to the solar system's past and future. It formed in chaos, may have migrated outward, captured Triton, shaped the Kuiper Belt, and will continue orbiting as the sun slowly changes over billions of years. The blue planet at the edge is not outside history. It is one of history's survivors. Neptune's storms are frightening because they challenge the way we expect giant planets to behave. Jupiter's Great Red Spot is famous because it has endured for so long. It is like a scar on the planet, a storm that has become part of Jupiter's identity. Saturn's hexagon is strange because it forms an almost geometric pattern around the North Pole. Uranus is unsettling because it rotates on its side, its seasons stretched into extreme patterns. But Neptune's storms feel different. They are powerful, dark, and temporary. The Great Dark Spot was one of Voyager 2's most haunting discoveries. In the images, it appeared as a huge shadowy oval, a deep atmospheric vortex set against the blue cloud tops. It was similar in concept to Jupiter's Great Red Spot, but not in behavior. It did not remain visible for centuries. By the time Hubble looked for it again, it was gone. Later dark spots appeared elsewhere. This suggests Neptune's atmosphere can produce immense vortices that live, move, and die on timescales much shorter than Jupiter's famous storm. This is important because it means Neptune's visible face is not permanent. The Neptune seen by Voyager in 1989 was not the Neptune we see now. The storms changed. The clouds changed. The color presentation in some images even changed as scientists reprocessed data and better understood the planet's true appearance. Many classic images show Neptune as a deep, saturated blue, partly because the images were processed to reveal features. More recent work suggests Neptune and Uranus may look more similar in true color than popular images once implied. That does not make Neptune less mysterious. In some ways, it makes it more mysterious. Because the image in our minds is not the whole truth. Neptune is not simply the perfect dark blue planet from posters and documentaries. It is a dynamic ice giant whose colors, storms, and cloud patterns require careful interpretation. Methane absorbs red light and contributes to the blue appearance, but the exact shade depends on atmospheric haze, clouds, and how images are processed. That means even its beauty contains a hidden complexity. The planet we think we know is partly a scientific reconstruction. The dark spots themselves are still being studied. Scientists think they are high-pressure systems, or vortices in Neptune's atmosphere, related to patterns of circulation and cloud formation. Bright companion clouds often appear nearby, likely made of methane ice crystals forming as air is forced upward and cools. On Earth, mountains can force air upward, creating clouds. On Neptune, a storm system can create conditions where bright clouds hover around a dark vortex like ghostly markings around a wound. But Neptune has no solid surface mountains beneath these storms. Its atmosphere is the landscape. The storms move through layers of gas, guided by wind bands and internal dynamics. They can drift in latitude. They can be stretched by winds. They can be pulled apart. They can vanish. The whole planet becomes a kind of fluid battlefield, with immense systems forming and dissolving without a surface to anchor them. That is one of the strangest things about weather on giant planets. On Earth, weather is shaped by oceans, continents, mountains, forests, deserts, and ice caps. On Neptune, the weather is shaped by depth, rotation, internal heat, and atmospheric chemistry. There are no continents to break the wind, no solid ground to stop a storm, no ocean surface in the familiar sense. Everything is fluid motion layered over deeper fluid motion. A storm on Neptune is not something passing over a world. It is the world expressing itself. The comparison between Neptune and Uranus may be one of the most important unsolved stories in planetary science. At first, the two planets seem like siblings. Both are ice giants. Both are similar in size. Both have hydrogen, helium, and methane in their atmospheres. Both are distant, cold, and bluish. But when scientists look more closely, the differences become striking. Neptune is more massive and denser. It emits significantly more internal heat. Its atmosphere shows stronger visible weather activity. Its winds are more extreme. Uranus, by contrast, appears strangely muted in internal heat, perhaps because of an ancient impact, unusual interior layering, or inhibited convection. This matters because two planets that look similar can have very different internal lives. That is a lesson for exoplanets as well. A distant telescope might see two planets with similar size and mass and assume they are alike. But Neptune and Uranus warn us that hidden histories matter. A giant impact billions of years ago, a difference in formation location, a variation in internal layering, or a change in heat transport can shape a planet for the rest of its life. Neptune is terrifying because it shows that a planet's face is not enough. You need its history, you need its heat, you need its magnetic field, you need its moons. Without those, the planet remains a mask. The cold of Neptune is another kind of terror. When we think of dangerous planets, we often imagine heat. Venus is terrifying because it is hot enough to melt lead. Mercury is terrifying because its day side can become brutally hot. Some exoplanets are so close to their stars that rock may vaporize and fall as rain. Heat is easy to fear because heat feels active. It burns, it consumes, it destroys quickly. But Neptune is terrifying in the opposite direction. It is a world of deep cold, weak sunlight, and long darkness. The upper atmosphere of Neptune is incredibly cold. The planet sits so far from the sun that it receives only a tiny fraction of Earth's solar energy. The warmth that makes Earth habitable is almost gone there. If you could float above Neptune's cloud tops in a perfectly protected spacecraft, you would be in a place where the sun is distant, the sky is black, and the planet below is a frozen blue giant with no surface to save you. Cold changes everything. Materials become brittle, chemical reactions slow, solar power becomes weak, human survival becomes dependent on insulation, nuclear energy, and constant engineering. A mission to Neptune would be nothing like a mission to Mars. Mars is hard, but it is still close enough that sunlight can power rovers, and communications delays are manageable. Neptune is so far away that sunlight is feeble, and radio signals take hours. A spacecraft there must be almost entirely independent, carrying its own heat, power, and patience. And yet, Neptune is not cold all the way down. This is where the planet becomes stranger. Under the cold clouds, the interior is hot. Neptune is an ice giant, but that does not mean it is frozen solid. The deeper you go, the pressure and temperature rise dramatically. The planet may contain a hot, dense mantle of water, ammonia, and methane, possibly forming exotic fluids under conditions far beyond normal experience. Scientists think there might be superhot water beneath the visible atmosphere, kept from boiling by immense pressure. So Neptune combines extremes: cold above, heat below, darkness outside, motion inside. This makes it different from a frozen moon or a dead asteroid. Neptune is not simply cold and inert. It is cold on the surface of its atmosphere, but powered from within. It is a planet where the outer layers face the weakest sunlight of any major planet, while deeper layers may hold enough heat to drive atmospheric violence for billions of years. This contrast is part of what makes Neptune feel alive in the wrong way. A frozen-looking planet should not have such powerful winds. A remote world should not have so much weather. A calm blue sphere should not be hiding internal energy strong enough to keep its atmosphere restless. But it does. Neptune radiates more energy than it receives from the sun. That internal heat is one of the central clues to its behavior. Where does it come from? Some of it is likely leftover heat from formation. When giant planets formed, gravity pulled material together, and that collapse released energy. Some heat can remain trapped inside for billions of years. Some may come from slow gravitational contraction, as the planet very gradually settles and releases energy. The exact details are complex, especially when we compare Neptune with Uranus, which is similar in size and composition, but emits much less internal heat. That difference between Uranus and Neptune remains one of the great puzzles of the ice giants. Neptune's cold is frightening because it is not simple. It is not the cold of a dead world. It is the cold skin of a deep, active, pressurized planet that refuses to be quiet. Triton's geysers deserve to be imagined slowly. On Earth, a geyser is already a strange thing. Water heated underground, pressure building, then eruption into the air. On Triton, the word geyser becomes almost alien. The surface is covered in frozen nitrogen. The temperature is so low that gases familiar to us can become frost. The atmosphere is thin, the sunlight is weak, and yet dark material can be thrown upward, rising kilometers above the surface before falling back in streaks. Voyager saw evidence of these plumes, and suddenly Triton became more than a cold moon. It became active. It became a place where the surface can breathe material into space. The plumes are not comforting. They are reminders that even frozen worlds can have internal and surface processes that surprise us. A moon can look dead and still erupt. A place can be nearly as cold as physically imaginable for a natural solar system surface and still change. This is one of the great themes of the outer solar system. Io erupts in fire. Europa hides in ocean. Enceladus sprays water into space. Titan has methane lakes. Triton has nitrogen geysers. The farther we go from the sun, the more we learn that cold worlds are not necessarily dead worlds. They are different worlds, operating under rules we are only beginning to understand. Neptune's interior may be one of the strangest environments in the solar system. We cannot see it directly. We cannot drill into it. We cannot send a probe all the way down and expect it to survive. Everything we know is inferred from mass, radius, gravity, atmosphere, magnetic field, heat emission, and models of how materials behave under extreme pressure. But those models suggest Neptune is not just a larger version of Earth or a smaller version of Jupiter. It is something else. It is an ice giant. That term can be misleading. Ice giant does not mean Neptune is made of ordinary ice. It means that, compared with Jupiter and Saturn, Neptune contains a much higher fraction of heavier, volatile materials, such as water, methane, and ammonia. In the early solar system, these substances could freeze into ices far from the sun, so scientists call them ices in planetary formation. But inside Neptune, the pressure and temperature transform them. Imagine water under pressure so enormous that it cannot behave like the water in oceans. Imagine methane and ammonia mixed into a hot, dense fluid. Imagine layers where chemistry, electricity, and phase changes create environments we have no direct earthly equivalent for. There may be regions where water becomes superionic, a strange state in which oxygen atoms form a lattice, while hydrogen ions move through it, allowing electrical conductivity. Scientists discuss such phases in the context of ice giants because they could help explain unusual magnetic fields. The exact interior structure of Neptune remains uncertain, but the possibilities are exotic. This matters because Neptune's magnetic field is bizarre. On Earth, the magnetic field is generated by motion in the planet's liquid outer core. The magnetic axis is tilted relative to the rotation axis, but not wildly so. On Neptune, the magnetic field is strongly tilted, about 47 degrees from the rotation axis, and offset from the planet's center. That means as Neptune rotates, its magnetosphere wobbles dramatically through space. It is not the neat centered dipole people often imagine when they picture a planetary magnetic field. This is terrifying in a subtle way. Magnetic fields are invisible, but they shape charged particles, radiation belts, auroras, and the interaction between a planet and the solar wind. Neptune's field being tilted and offset suggests the dynamo may not be deep in a central metallic core like Earth's, but perhaps in a shell of electrically conducting fluid inside the planet. The magnetic field becomes a clue that Neptune's interior is not organized in the way our intuition expects. A spacecraft near Neptune would not just face distance and cold. It would face a magnetic environment that changes dramatically with rotation. Charged particles would move through a magnetosphere that twists and pulses. The solar wind is weak at Neptune compared with Earth, but the magnetic field still creates a complex region of space around the planet. And because Neptune has moons and rings, particles and dust may interact with that environment in ways we still need to understand. The interior also matters because it may explain Neptune's heat. The planet gives off more energy than it receives from the sun. That means some internal reservoir is leaking energy into space. But why Neptune does this so strongly while Uranus does not is still not fully solved. Uranus and Neptune are often called twins, but they are not identical. Neptune is slightly smaller but more massive. It is denser. It has stronger internal heat. It has more obvious atmospheric activity. Something about its formation, impact history, layering, or interior mixing may have made it different. In that sense, Neptune is not only a planet, it is a locked room. We see the clouds, we measure the gravity, we detect the magnetic field, we record the heat. But the real machinery is hidden thousands of kilometers below the visible atmosphere, in pressure and chemistry no human has ever touched. Neptune's atmosphere also raises questions about chemistry under conditions that are hard to reproduce. At the cloud tops, methane plays a visible role. It absorbs red light and helps give Neptune its blue appearance. It can freeze into bright ice clouds high in the atmosphere. Deeper down, methane is part of a much more complex mixture involving hydrogen, helium, water, ammonia, and other compounds. Under high pressure, these substances may separate, react, conduct electricity, and contribute to planetary structure in ways that are still being explored. Some scientists have even discussed the possibility that deep inside ice giants, carbon from methane could form diamond-like structures under extreme pressure. The phrase diamond rain is often used in popular science, though the exact processes and conditions are complex. The important point is not the cinematic image of diamonds falling through the planet, but the fact that Neptune's interior chemistry is extreme enough to make ordinary molecules behave in extraordinary ways. This is another reason Neptune is unsettling. Its beauty is simple from far away, but its chemistry is not. A blue dot becomes a laboratory of high-pressure physics. The deeper you go, the less useful everyday experience becomes. Ice is not ice. Water is not water. Air is not air. Even familiar substances become alien. One of Neptune's most unsettling features is that it refuses to fit the simple story of the outer solar system. If you lined up the giant planets by distance from the sun, you might expect them to become calmer as you go outward. Jupiter is huge and stormy. Saturn is ringed and dynamic. Uranus is cold and oddly tilted. Neptune, being farthest away, might seem like it should be the quiet endpoint, the place where the solar system slowly fades into stillness. But Neptune is not the quiet endpoint. It is active. Its atmosphere is violent. Its moon Triton is geologically strange. Its rings contain arcs that remain clumped instead of spreading evenly. Its magnetosphere is tilted and offset. Its discovery was mathematical. Its exploration was brief. Everything about Neptune suggests that the outer edge of the planetary solar system is not simple, not dead, and not fully understood. This is especially important when we think about the early solar system. Neptune may not have formed exactly where it is now. Many models suggest the giant planets migrated after formation, reshaping the outer solar system. Neptune's movement may have disturbed icy bodies, sculpted the Kuiper belt, captured Triton, and helped scatter objects into distant orbits. In other words, Neptune may look like a distant planet minding its own business, but its gravity has helped shape the architecture of the solar system's frontier. A planet does not have to be close to be powerful. Neptune's gravity reaches into the Kuiper belt, where countless icy bodies orbit beyond the major planets. Some are locked in resonances with Neptune. Pluto, for example, is in a 3.2 orbital resonance, meaning it orbits the Sun twice for every 3 orbits Neptune completes. This resonance prevents close encounters, even though Pluto's elliptical orbit sometimes brings it closer to the Sun than Neptune. The two worlds are choreographed by gravity, so they never collide. That relationship is beautiful, but it also shows Neptune's hidden control. From billions of miles away, Neptune organizes distant objects. It marks the boundary between the familiar planetary system and the realm of icy leftovers. It is not just another planet, it is a gatekeeper. Beyond it lies the Kuiper belt, scattered disk objects, comets, dwarf planets, and the slow fade toward interstellar space. Neptune stands at the last bright threshold before the solar system becomes less like a family of planets and more like a vast field of remnants. This gives Neptune a mythic quality, but the science is real. It is the last major planet. It is the farthest known giant. It is the only planet discovered because of mathematics. It guards a region filled with primitive icy bodies left from the early solar system. It captured a moon that probably once belonged to that distant realm. It has rings, storms, internal heat, and a magnetic field that hints at exotic processes below. And yet, we have only visited it once. That single fact should stay with you. Humanity has sent orbiters to Mars, Jupiter, and Saturn. We have landed on Venus, Mars, Titan, asteroids, and comets. We have flown past Pluto. But Neptune, one of the main planets, has only been seen up close by Voyager 2 during a fast flyby. The images we have are priceless, but they are snapshots. A whole world, a whole system, reduced to a brief encounter. Neptune is terrifying partly because it remains unfinished in our knowledge. It is not just distant in space. It is distant in understanding. The darkness around Neptune is not empty in the way people imagine. Space near Neptune contains magnetic fields, charged particles, dust, moons, rings, sunlight, infrared radiation, and gravitational resonances. It is sparse, cold, and quiet compared with the inner solar system, but it is not nothing. The planet carves out a region around itself, controlling material and motion. Its moons orbit within that domain. Its rings trace thin paths through it. Its magnetosphere responds to the solar wind even at that distance. This matters because the outer solar system is often described as a void, but the word void can mislead us. The region is not empty. It is simply operating at a scale and density far outside human senses. A dust grain, a charged particle, a faint ring arc, or a small moon may seem insignificant, but each one participates in the system's physics. Neptune is surrounded by structure, but the structure is dark and subtle. That subtlety is part of the fear. Near the sun, everything is brighter and easier to see. At Neptune, even important things can hide in faintness. The rings are faint. The moons are small. The sunlight is weak. The signals are delayed. The storms are distant. The entire system feels like it is half hidden by its own remoteness. Then there is Triton. If Neptune itself is terrifying, Triton is the twist that makes the system feel almost unreal. Triton is Neptune's largest moon, and it is unlike almost any other major moon in the solar system. Most large moons orbit their planets in the same direction that their planets rotate. This makes sense if they formed from a disk of material around the planet. But Triton moves in the opposite direction. It has a retrograde orbit. that one fact is a clue to a violent past. Scientists think Triton was not born as Neptune's moon. It was probably a Kuiper Belt object, a cousin of Pluto, captured by Neptune's gravity long ago. Imagine a frozen world wandering the outer solar system, independent, orbiting the sun. Then, through a gravitational encounter, Neptune steals it. Capture on that scale is not gentle. Triton's arrival may have disrupted or destroyed an earlier system of Neptune's moons, reshaping everything around the planet. The calm blue planet may have a history of gravitational violence. And Triton itself is strange. It is extremely cold, with surface temperatures around -391 degrees Fahrenheit, or -235 degrees Celsius. That is so cold that nitrogen freezes onto the surface. Much of Triton is covered with nitrogen ice, giving it a bright reflective surface. It is one of the coldest objects ever visited by a spacecraft. At first, you might expect such a world to be dead, locked in deep freeze forever. But Voyager 2 saw geysers, active geysers. On a moon almost impossibly cold, Voyager saw dark plumes rising from the surface and streaking material downwind. Triton became one of the few known geologically active bodies in the solar system. That is the kind of discovery that changes how a place feels. It means that even at Neptune, even in that extreme cold, even on a captured moon at the edge of the planetary system, something is still happening. The geysers may be driven by sunlight warming nitrogen ice in a greenhouse-like process beneath translucent surface layers, or by other cryovolcanic and seasonal processes. They are not volcanoes like Io's molten sulfur and rock, but they are still eruptions from a frozen world. They show that activity does not require warmth in the Earth-like sense. In the outer solar system, geology can be made of ices, gases, pressure, sunlight, and slow seasonal change. Triton's surface is young in places. Voyager images showed smooth volcanic plains, mounds, pits, and strange terrain that suggests resurfacing. That means Triton's surface has been altered over time, erasing many craters. A dead icy body should preserve impacts for billions of years. A resurfaced body has processes that renew or cover its face. Triton is not simply an ancient frozen fossil. It is a captured world with a complicated interior and surface history. And Triton's future may be just as dramatic as its past. Because it orbits retrograde, tidal interactions with Neptune are slowly changing its orbit. Over extremely long timescales, Triton may spiral inward. Eventually, it could be torn apart by Neptune's gravity or collide with the planet, depending on how its evolution unfolds. That would create a catastrophic transformation of the Neptunian system. A captured moon, stolen from the outer solar system, may one day be destroyed by the planet that captured it. That is why Triton makes Neptune more terrifying. The system is not peaceful. It is a frozen crime scene, still active after billions of years. If humans ever watched Neptune from orbit through a spacecraft camera, the experience would be strangely slow and strangely fast at the same time. The planet rotates in about 16 hours, so clouds and storms would move across the disk in less than an Earth day. Atmospheric features could be tracked, measured, and compared. The magnetosphere would sweep around. Moons would move in their orbits. Rings would reveal structure in changing light. On that scale, Neptune would feel dynamic. But the larger cycles would be slow. Seasons last decades. Internal evolution unfolds over millions and billions of years. Triton's orbital future stretches into deep time. The Kuiper Belt architecture reflects ancient migration. Neptune operates on multiple clocks at once, hours for rotation, days for moon motion, decades for seasons, centuries for orbits, and billions of years for planetary history. That layering of time is one of the reasons planets are so fascinating. They are not objects frozen at a single moment. They are processes. Neptune is a process in blue, rotating, radiating, storming, cooling, orbiting, pulling on moons, shaping distant objects, and carrying ancient history inside its atmosphere and gravity. Neptune's rings are another quiet mystery. When people think of rings, they think of Saturn. Saturn's rings are bright, wide, and stunning, visible even through modest telescopes. They look like the signature of elegance in the solar system. Neptune's rings are nothing like that. They are faint, dark, dusty, and difficult to see. They were confirmed by Voyager 2, and they make the planet feel stranger because they do not behave in the simple way many people expect. Neptune has several main rings. They are named Gala, Leverrier, Lassell, Arago, and Adams, but the most famous features are the ring arcs in the outer Adams ring. These arcs are clumps of material with names like Liberté, Égalité, Fraternité, and Courage. The strange thing is that ring material orbiting a planet should tend to spread out over time. Particles at slightly different distances orbit at slightly different speeds, causing clumps to smear around the planet. Yet Neptune's arcs remain concentrated. Something is holding them there. Scientists think the gravity of a nearby moon, Galatea, helps confine or stabilize the arcs. This is another example of how Neptune's system is full of subtle gravitational structure. From a distance, the planet looks simple. Up close, it has rings, moons, arcs, resonances, and interactions that create patterns we are still working to understand. The rings are dark. They do not shine like Saturn's icy rings. They are likely made of dusty material, perhaps coated with radiation-darkened compounds. Around Neptune, sunlight is already weak, and the rings are faint even by the standards of outer solar system observation. They are like shadows around a blue planet, fragile and easy to overlook. That makes them eerie. They are not glorious like Saturn's rings. They are not obvious symbols of beauty. They are more like traces, thin, dark lines around a remote world, held together by gravity and time. They remind us that Neptune is not just a planet, but a system. It has moons, rings, arcs, and dust, all moving in the deep cold. And because Neptune is so far away, these features are hard to monitor. A ring system close to Earth would be studied in exquisite detail. At Neptune, every observation is difficult. Telescopes must push their limits. Spacecraft missions require decades of planning and travel. The result is that Neptune's rings remain less familiar than they should be. They are part of a major planet, yet most people barely know they exist. This unfamiliarity matters. The terrifying thing about Neptune is not always violence. Sometimes it is neglect. It is the realization that one of the 8 major planets has whole structures around it that remain obscure to the public and incompletely explored by science. The rings are not simply decorative. They are evidence of collisions, moon interactions, dust production, gravitational confinement, and the long-term evolution of the system. Every ring particle is a clue. Every arc is a question. And around Neptune, even the quiet details feel like they are hiding something. The phrase "more terrifying than you think" works especially well for Neptune because most people do not think about Neptune very much at all. Jupiter has a clear public identity. Largest planet, great red spot, giant gravity, many moons. Saturn has rings. Mars has aliens, rovers, and future colonies. Venus has heat and pressure. Mercury is closest to the Sun. Uranus is tilted and often treated as a joke. Neptune is usually just the last one, the blue one, the distant one. That lack of attention hides its drama. Neptune has the fastest winds. It has mysterious heat. It has a strange magnetic field. It has a captured active moon. It has dark storms that vanish. It has rings with arcs. It sits at the gravitational edge of the classical planetary system. It was discovered through mathematics. It has been visited once. Almost every part of its story is stronger than its public reputation. So, the title is not exaggeration. Neptune really is more terrifying than many people think, because many people think of it as a quiet blue endpoint. The truth is richer, colder, darker, and far more violent. Neptune's magnetosphere adds another layer of strangeness. A magnetosphere is the region around a planet controlled by its magnetic field. It acts like a shield and a trap. It can deflect charged particles from the solar wind, guide radiation belts, create auroras, and shape how a planet interacts with space around it. Earth's magnetosphere helps protect our atmosphere and surface from some charged particles, making it an important part of our planet's habitability. But Neptune's magnetic field is not neatly aligned. Its magnetic axis is tilted by about 47 degrees compared with its rotation axis. It is also offset from the center of the planet. This means Neptune's magnetosphere does not rotate like a simple, centered field. It wobbles dramatically as the planet spins. Imagine a lighthouse beam that is not only tilted, but mounted off-center, sweeping space in a strange, uneven pattern. That is not a perfect metaphor, but it gives a feeling for how odd Neptune's magnetic environment can be. Why is it like this? The answer likely lies deep inside the planet. Earth's magnetic field is generated by the motion of molten iron in the outer core. But Neptune probably does not have an Earth-like iron dynamo dominating its field. Instead, its magnetic field may be generated in a shell of electrically conducting fluid, perhaps involving water, ammonia, methane, and ionic or exotic phases under extreme pressure. If the dynamo region is not centered and symmetric, the magnetic field can become tilted and offset. This is one of the clues that ice giants are fundamentally different from rocky planets and gas giants. Jupiter's magnetic field is enormous and dangerous, but it is easier to imagine as a giant version of a planetary field. Neptune's is more geometrically strange. It suggests a planet whose interior is layered and complicated in ways we cannot directly see. The field becomes a shadow cast by hidden machinery. For a spacecraft, that matters. A mission near Neptune would need to understand charged particles, magnetic field orientation, and how the field interacts with moons and rings. Radiation at Neptune is not like Jupiter's devastating radiation belts, but the magnetosphere is still a dynamic environment. It also tells scientists about the planet's internal structure, which is one of the most important reasons to study Neptune up close. The magnetosphere may also interact with Triton and other moons. Charged particles can alter surfaces over time, darkening materials, breaking molecules, and creating chemical changes. In the outer solar system, radiation is part of geology in slow motion. It can change the colors of icy surfaces, drive chemistry, and affect tenuous atmospheres. Around Neptune, this process is part of the hidden life of the system. And there is another unsettling aspect. Magnetic fields are invisible to human senses. You could look at Neptune and see only blue clouds. You would not see the tilted magnetic structure sweeping around it. You would not see charged particles guided by field lines. You would not see the deep interior motions generating the field. The most important structures around the planet would be unseen. That makes Neptune feel like a world with two faces. The visible one, blue, distant, quiet. The invisible one, tilted, shifting, electrically active, and controlled by physics buried far below the clouds. If a human mission ever tried to visit Neptune, the danger would begin long before arrival. The first problem is time. Neptune is so far away that reaching it with current technology is a major challenge. Voyager 2 took 12 years to reach Neptune, but it used a rare planetary alignment and gravity assists from the outer planets. A dedicated mission could take many years, potentially more than a decade, depending on trajectory, propulsion, and mission design. This is not like sending a spacecraft to the Moon in days or to Mars in months. Neptune is a destination measured in deep patience. During that journey, sunlight becomes weaker and weaker. Solar panels, so useful in the inner solar system, become less practical. By the time you reach Neptune, solar energy is tiny compared with Earth's orbit. A mission would likely need nuclear power, such as radioisotope thermoelectric generators or future nuclear systems. That means the spacecraft must carry its own long-lasting energy source. It must survive cold, radiation, dust, mechanical aging, and the slow degradation of systems over many years before the main science even begins. Then there is communication. At Neptune, radio signals take hours to travel between the spacecraft and Earth. There is no real-time control. Every command must be planned, sent, and waited on. Every answer comes back long after the event. If something goes wrong, engineers cannot joystick the spacecraft out of danger. They must design autonomy and reliability into the mission from the beginning. This makes Neptune feel lonely in a very practical way. A spacecraft there is not merely far from Earth emotionally. It is far from Earth operationally. It has to think in slow motion with its creators. It has to execute commands in a region where help is always hours away and physical rescue is impossible. If the mission were an orbiter, the challenge becomes even greater. To orbit Neptune, a spacecraft must slow down enough to be captured by the planet's gravity. That requires fuel, aero capture, gravity assists, or advanced mission design. A flyby is easier because the spacecraft can simply pass through the system at high speed. But a flyby gives only a snapshot. An orbiter would transform our understanding by watching Neptune's weather, magnetosphere, rings, and moons over years. It would also be one of the most difficult planetary missions ever attempted. Imagine arriving after a journey of more than a decade. The sun is now just a brilliant star. Earth is invisible to the eye. Neptune fills the view, blue and enormous, with dark storms moving through its atmosphere. Triton circles in retrograde motion, a captured frozen world. Faint rings arc around the planet. Everything is beautiful, but every system on the spacecraft is old, cold, and far from repair. That is the engineering terror of Neptune. Not sudden destruction, but distance. Distance makes every problem worse. A stuck valve, a failing heater, a software glitch, a weakening power supply, a thruster issue, a communication anomaly. Near Earth, these are emergencies. At Neptune, they are existential. There is no spare part, no astronaut repair, no quick command response, no second spacecraft nearby. The planet is terrifying because it sits beyond ordinary rescue. To study Neptune properly, we would have to send a machine into one of the loneliest environments humanity has ever explored and trust it to survive for years. Voyager 2's encounter with Neptune remains one of the most important moments in planetary exploration. By the time Voyager reached Neptune in August 1989, it had already transformed our understanding of the outer solar system. It had flown past Jupiter, Saturn, and Uranus. It had seen volcanoes on Io, intricate rings around Saturn, strange moons, magnetic fields, and worlds no human had ever seen close up. Neptune was the final planetary target of the Grand Tour. And then, after more than a decade of travel, the spacecraft arrived. It did not stop. It could not stop. Voyager 2 flew past Neptune at high speed, gathering as much data as possible during a brief window. It photographed the planet, studied its atmosphere, measured its magnetic field, observed its rings, and then flew by Triton. That flyby gave humanity its first and only close-up look at Neptune's system. Everything had to work. There was no second chance. The encounter revealed a planet far more active than expected. Scientists saw the Great Dark Spot. They saw high-speed winds and bright clouds. They confirmed rings. They discovered new moons. They measured the strange magnetic field. They saw Triton's young terrain and geyser-like plumes. Neptune and Triton went from distant points of light to actual worlds with weather and geology. But the encounter also left behind a haunting limitation. Voyager was fast. It gave us a masterpiece of a glimpse, but only a glimpse. Imagine trying to understand Earth from a single flyby. You might see clouds, continents, oceans, storms, city lights if the geometry allowed it. But you would not understand seasons, climate cycles, ocean currents, plate tectonics, biology, or human civilization. You would have clues, not comprehension. That is what Neptune remains in many ways, a world of clues. Since Voyager, telescopes have continued the work. Hubble has tracked storms appearing and disappearing. Ground-based observatories have studied Neptune's atmosphere in different wavelengths. Modern processing has improved our understanding of its color and cloud structure. But there is no substitute for being there. A spacecraft in orbit could watch storms form, drift, and vanish. It could map the magnetic field over time. It could study rings and arcs up close. It could repeatedly observe Triton and search for changes. The absence of such a mission is one reason Neptune feels almost mythological. It is not that science ignores it. Scientists deeply want to understand it. But the distance makes everything difficult. Launch windows, travel time, power, budget, mission lifetime, communications, orbital insertion, and instrument design all become major obstacles. Neptune is not inaccessible in principle, but it is hard enough that humanity has not returned since 1989. So our knowledge of Neptune is like a partially lit room. Voyager opened the door. For a moment, light poured in. Then the door almost closed again, leaving us with images, measurements, and decades of questions. Neptune is also terrifying because it reminds us how misleading beauty can be. The planet is beautiful. There is no way around that. Its blue color, its distant setting, its faint rings, its mysterious storms, and its place at the edge of the planetary solar system all give it a haunting elegance. If you saw a high-resolution image of Neptune without knowing the facts, you might think it was peaceful. But beauty in space does not mean safety. Nebulae are beautiful, but they are vast clouds of gas shaped by radiation, stellar death, and star formation. Galaxies are beautiful, but they contain supermassive black holes, colliding stars, and regions of lethal radiation. Saturn's rings are beautiful, but they are made of countless icy fragments moving at orbital speeds. Neptune is beautiful, but its atmosphere would destroy any unprotected visitor. Its winds are extreme. Its pressure increases without mercy, and its moons and rings tell stories of capture and violence. This is one of the core lessons of astronomy. The universe does not need to look frightening to be dangerous. Neptune's terror is not obvious like a lava world or an exploding star. It is quieter. It comes from realizing that the planet's calm appearance is a surface illusion. Beneath that blue color is a world with no surface, no breathable air, no warmth, no rescue, no familiar landscape, and no simple weather. Everything about it is hostile to human experience. Even the color is part of the illusion. The blue comes largely from methane in the atmosphere, which absorbs red light and lets blue light dominate. But Neptune's actual appearance is not the oversaturated deep blue many people remember from older images. Science refines images, corrects colors, and reveals details. Neptune is not lying exactly, but our perception of it is shaped by processing, distance, and expectation. The planet people imagine may be more dramatic than the one a spacecraft camera would see in natural color, yet the real planet is still more terrifying than the image. That difference matters for storytelling. A fiery planet looks dangerous immediately. A black hole looks dangerous because we already know it represents gravity and doom. Neptune looks gentle. Its danger is hidden under calm color. That makes it a stronger kind of cosmic horror. It is the ocean that looks smooth from above, but has impossible currents below. It is the quiet room with machinery behind the walls. It is the planet that seems to sleep while winds roar faster than sound. And it is not alone. Uranus and Neptune together represent an entire class of planets we barely understand. Ice giants may be common in the galaxy. Many exoplanets appear to fall into sizes between Earth and Neptune, including mini-Neptunes and super-Earths. Understanding Neptune is not just about one planet. It may help us understand countless worlds orbiting other stars. If we do not understand the ice giants in our own solar system, how can we fully understand similar planets light years away? So Neptune is not only a destination, it is a key, a beautiful, distant, dangerous key to one of the most common kinds of planetary architecture in the universe. One of the most powerful ways to feel Neptune's terror is to imagine falling into it, not because any human could survive such a fall, but because the thought experiment reveals what the planet really is. You begin above the cloud tops. The sun is tiny, a bright point in the black sky. Beneath you, Neptune is not a solid world, but a vast blue curve. There is no continent, no ocean, no cratered surface, only atmosphere. At first, the descent might almost seem peaceful from inside an imaginary indestructible capsule. Blue haze above, deeper blue below, streaks of methane clouds moving at incredible speed. Then the wind begins to matter. Your capsule is caught in atmospheric currents far stronger than anything on Earth. It is pushed sideways at hundreds of miles per hour, then faster. The sky around you is not empty. It is filled with hydrogen, helium, methane, and deeper chemical layers. The pressure rises. What began as an outer atmosphere becomes a crushing environment. Every instrument records increasing stress. There is still no ground. This is the part the human mind resists. Falling should lead to impact. Descent should end. But on Neptune, there is no clear surface waiting below. Instead, the atmosphere thickens. The pressure rises from something a spacecraft can endure to something that deforms and destroys. The temperature changes. Chemical layers shift. Clouds give way to deeper fluids. The boundary between atmosphere and interior becomes less like a line and more like a transformation. Eventually, your imaginary capsule reaches pressures where ordinary materials fail. If it were not magical, it would be crushed, heated, chemically attacked, and lost. Communication would become impossible. Light from above would vanish. The world outside would become a dense, dark, super-pressurized medium. Farther down, the deep interior might contain hot mixtures of water, ammonia, and methane. materials behaving in exotic ways under giant planet pressure. And still, in some sense, you would not have reached a surface. You would have entered the planet. This is why Neptune is terrifying. In a way, rocky planets are not. A rocky planet can be hostile, but it remains comprehensible. Venus has ground. Mars has dust. Mercury has craters. Neptune is more like an abyss given planetary form. You do not land on it. You disappear into it. The same is true of Jupiter and Saturn in broad terms, but Neptune's remoteness and cold give the descent a different emotional texture. Jupiter feels overwhelming because it is enormous and radiant with power. Saturn feels magnificent and alien. Neptune feels like falling into the end of sunlight. A blue descent into a place where the solar system is fading, but the planet itself is still violent. There would be no dramatic final view of ground rushing up. No last mountain, no horizon, only pressure, darkness, and depth. And that may be one of the most frightening things a planet can be. Neptune's relationship with the Sun is one of the strangest parts of its identity. The Sun is the central power source of the solar system. It holds the planets in orbit. It lights them. It warms them. It drives weather, climate, photosynthesis, and the basic conditions that make Earth alive. The closer you are to the Sun, the more obvious its power becomes. Mercury is scorched. Venus is trapped in a runaway greenhouse. Earth is warm enough for oceans. Mars is cold, but still touched by sunlight. Then you move outward. At Jupiter, sunlight is weaker, but still enough to illuminate its cloud bands brilliantly. At Saturn, the sun is smaller, but the rings still shine. At Uranus, the light is colder, more distant, more subdued. At Neptune, the sun is still there, but it no longer feels like the warm parent star of Earth. It feels like a remote authority. This changes the mood of the planet. Neptune is part of the solar system, yet it feels nearly exiled from the sun's comfort. It receives light, but not warmth in the way Earth understands warmth. It orbits faithfully, but at such a distance that a year lasts 165 Earth years. Its seasons move so slowly that human history seems fast by comparison. Civilizations rise and fall during a single Neptunian season. And yet, the sun still matters. Even weak sunlight can affect the upper atmosphere over long timescales. It can influence chemistry, seasonal changes, and the behavior of Triton's nitrogen frost. It can warm surface layers just enough to drive activity on a moon at temperatures that seem impossibly cold. In the outer solar system, small inputs over long times can create real effects. The sun is diminished, not absent. This subtlety is important. Neptune is not a rogue planet. It is not lost in interstellar darkness. It still belongs to the sun, but it belongs from the edge. It is the last major world still held in the familiar planetary family, and that makes it a boundary object. It is both connected and remote. It is both illuminated and dark. It is both part of our system and a preview of the deep cold beyond. This boundary feeling is one reason Neptune makes such a strong documentary subject. It is not just another planet. It is the final major planet before the solar system dissolves into smaller, colder, stranger populations of objects. After Neptune, there is no next giant planet. There are dwarf planets, Kuiper belt worlds, scattered objects, comets, and eventually the distant Oort cloud. The architecture becomes less familiar. The sun's grip continues, but the sense of planetary order fades. Neptune is the last blue door, and behind it is the outer darkness. That is why the planet feels more terrifying than people expect. Not because it is the biggest, or the hottest, or the most explosive. but because it sits at the edge of the known planetary realm, still active, still storming, still hiding secrets, while the sun itself begins to feel far away. Neptune's moon system tells a story of order disrupted. The other giant planets have moon systems that, in some ways, feel like mini solar systems. Jupiter has the Galilean moons, Io, Europa, Ganymede, and Callisto, each extraordinary in its own way. Saturn has Titan, Enceladus, Iapetus, and many others, surrounded by a magnificent ring system. Uranus has several major moons orbiting in the plane of its tilted equator, but Neptune's system is dominated by Triton, and Triton does not behave like a moon that calmly formed there. Its retrograde orbit suggests capture. That single event may have changed everything. If Neptune once had a regular moon system like Uranus, Triton's capture could have destabilized it. Existing moons may have collided, been ejected, or fallen into Neptune. Over time, Triton's orbit would have circularized through tidal interactions, releasing energy and reshaping the system. The Neptune we see today may be the aftermath of a violent rearrangement. This makes the system feel haunted. We do not see the original moons that may have existed. We see what survived. We see Triton, the captured giant. We see smaller moons, rings, arcs, and debris. It is like looking at a battlefield long after the battle ended, where the landscape has become quiet, but every structure still carries evidence of violence. Triton itself may be a captured dwarf planet. That idea changes its emotional meaning. It is not simply Neptune's moon. It may be a stolen world, a Pluto-like object that once belonged to the Kuiper Belt. Now it orbits backward around Neptune, frozen, active, and trapped. There is something almost tragic about that. A world from the outer darkness, pulled into orbit around the last giant planet, forever moving against the expected direction. And Triton is not dead. Its nitrogen atmosphere, icy surface, and geyser activity suggest ongoing processes. Seasonal changes may alter its thin atmosphere. Its surface reflects much of the sunlight that reaches it, making it bright despite the darkness. Dark streaks from geyser plumes mark the polar regions. The moon looks frozen, but it has breath, motion, and renewal. The other moons are smaller and less famous, but they matter. Neptune has a collection of inner moons, irregular moons, and distant companions. Some may be fragments of past collisions. Some may have been captured. Some help shape rings. Each one is a piece of the larger, dynamical story. Around Neptune, moons are not just accessories. They are evidence of capture, disruption, and gravitational control. This gives Neptune a different feeling from Saturn. Saturn's system feels grand and ornate. Jupiter's feels powerful and active. Neptune's feels colder, darker, and more mysterious, as if we are seeing the remains of a system altered by an intruder that became its dominant moon. The terror here is not immediate danger. It is deep time. It is realizing that planets are not static decorations. They capture, scatter, reshape, and destroy. Neptune may look calm now, but its moon system suggests a past filled with gravitational violence. And over billions of years, that violence is still written into the motion of Triton. The more we study Neptune, the more it becomes a mirror for things we do not understand about exoplanets. In the last few decades, astronomers have discovered thousands of planets orbiting other stars. Many of them are unlike anything in our solar system. Some are hot Jupiters, gas giants orbiting extremely close to their stars. Some are super-Earths, larger than Earth but smaller than Neptune. Some are mini-Neptunes, worlds with thick atmospheres and sizes between rocky planets and ice giants. These kinds of planets appear common in the galaxy. But our own solar system has no planet between Earth and Neptune in size. That creates a problem. If we want to understand mini Neptunes around other stars, we need to understand Neptune itself. We need to understand ice giant formation, atmospheres, interiors, magnetic fields, heat flow, and migration. Neptune is not just a distant curiosity. It is one of our best local examples of a planetary type that may be widespread in the galaxy. This makes our lack of close exploration more frustrating. We have only one flyby of Neptune and one flyby of Uranus. The two ice giants are the least explored class of major planets in our solar system, yet they may hold clues to some of the most common planets elsewhere. That means Neptune is scientifically valuable far beyond its own orbit. It is a nearby laboratory for understanding alien worlds. Its atmosphere can teach us how methane, hydrogen, helium, clouds, haze, and internal heat behave under low sunlight. Its interior can help us model water-rich and volatile-rich planets. Its magnetic field can reveal how dynamos work in exotic fluids. Its moon Triton can teach us about captured Kuiper Belt objects and icy geologic activity. Its rings and arcs can teach us about dust dynamics and moon interactions. In other words, Neptune is a complete planetary science system, and yet it remains mostly unexplored. This is the kind of fact that should bother us, not emotionally, perhaps, but intellectually. We live in a time when telescopes can detect planets hundreds of light years away, yet one of the main planets orbiting our own sun has never had an orbiter. Neptune is close enough to belong to us, but far enough to resist us. That resistance is part of its terrifying beauty. It reminds us that the solar system is still large. Not historically large, not metaphorically large, but practically large. Large enough that entire worlds can remain barely visited. Large enough that one spacecraft flyby can define public understanding for decades. Large enough that a mission launched by one generation might arrive when another generation is grown. Neptune teaches humility. It says, "You have explored the moon, Mars, and the inner solar system. You have flown past Pluto. You have built space telescopes and mapped exoplanets. But here, still within your own sun's domain, is a giant world you barely know." That is not failure, it is scale. If Neptune had a voice, it might not roar, it might whisper. That is because its danger is not the obvious danger of fire or impact. It is the quiet danger of distance, cold, pressure, and ignorance. Neptune does not need to explode. It does not need to threaten Earth. It does not need to be on a collision course. Its terror comes from existing exactly where it is, doing exactly what it does, while remaining almost unreachable. This is a different kind of fear. Human beings evolved on a warm, rocky surface under a bright sun. We understand land, sky, water, storms, mountains, and seasons. Neptune offers almost none of that. It is a world without ground, under a sun that has become a distant star, with winds faster than anything humans experience, with storms the size of planets, with a captured moon still erupting in the cold, and with an interior we can only model through physics. It is familiar enough to be part of our solar system, but alien enough to feel like another universe. This combination is powerful. If Neptune were completely fictional, it might be easy to dismiss. If it were close and well explored, it might feel less mysterious. But Neptune is real, distant, beautiful, dangerous, and underexplored. It sits at the edge of the planetary family like a blue secret, and every fact makes it stranger. The sunlight there is roughly 900 times weaker than on Earth. The winds can exceed 1,200 miles per hour. The great dark spot was large enough to contain Earth, and then it vanished. The magnetic field is tilted and offset. The largest moon orbits backward and may have been captured from the Kuiper belt. That same moon is so cold nitrogen freezes on its surface, yet it has active geysers. The rings have arcs that stay clumped against simple expectation. The planet emits more heat than it receives from the sun. No spacecraft has visited since Voyager 2. Taken separately, each fact is interesting. Together, they create a portrait of a planet that is far more disturbing than its calm appearance suggests. Neptune is not just a blue dot. It is a layered mystery where every answer opens another question. Why are the winds so fast? Why is its internal heat so strong compared with Uranus? What exactly happens deep inside an ice giant? How do its storms form and disappear? How did Triton change the system? What would an orbiter discover if it watched Neptune for 10 years? These questions matter because they are not merely trivia. They reach into planetary formation, atmospheric physics, interior chemistry, magnetic fields, and the history of the outer solar system. Neptune is terrifying because it is a reminder that even close to home, the universe has not become familiar. The unknown is not only beyond the stars. Sometimes it is the 8th planet from the Sun. Let us imagine a future mission. A spacecraft launches from Earth, perhaps using gravity assist to build speed. Years pass. It flies through the inner solar system, then beyond Jupiter, beyond Saturn, beyond Uranus. The Sun shrinks behind it. Solar panels become useless. Nuclear power keeps the instruments warm and alive. Engineers on Earth age while the spacecraft travels. Children who watch the launch grow into adults before arrival. Then Neptune appears. At first, it is a point, then a disk, then a world. The spacecraft begins to see cloud bands, storms, rings, and moons. Triton grows from a dot into a frozen sphere. The mission approaches the system, carrying decades of human curiosity into a region no machine has entered closely since 1989. If it is an orbiter, the most dangerous moment may be arrival. The spacecraft must slow down. Too fast, and it flies past forever. Too slow in the wrong way, and the mission fails. Every calculation matters. The burn must happen at the right time. The spacecraft is billions of miles away, executing instructions sent hours earlier from a planet that is now just a tiny invisible point near the Sun. If it succeeds, the reward is enormous. For the first time, humanity could watch Neptune instead of glimpsing it. We could see storms evolve from birth to death. We could map winds over seasons. We could measure heat flow. We could study the magnetosphere through many rotations. We could observe ring arcs up close. We could fly by Triton repeatedly, watching its geysers, mapping its surface, and searching for evidence of an internal ocean or cryovolcanic activity. A Neptune orbiter would rewrite textbooks. It would also change how the public feels about the planet. Voyager gave Neptune an identity, but an orbiter would give it a story. We would stop thinking of it as the blue dot at the end of the solar system and start seeing it as a dynamic world with weather, time, and change. That is what happened with Saturn during the Cassini mission. Saturn was always beautiful, but Cassini made it intimate. It revealed storms, moons, rings, geysers, lakes on Titan, and the complexity of a whole system. Neptune deserves that kind of exploration, but the difficulty is part of why it has not happened yet. Every mission competes with others. Mars, Europa, Titan, asteroids, the Moon, and space telescopes all have strong scientific reasons. Neptune is far, expensive, and slow. The return on investment is huge, but delayed. In a world of short attention spans and limited budgets, A mission that might take decades requires unusual commitment. This is why Neptune is not only a scientific challenge, it is a human challenge. Can we care about a world we may not see up close for decades? Can we build a mission whose greatest discoveries may arrive far in the future? Can we accept that some of the most important places in our solar system require patience beyond ordinary planning? Neptune asks us to think like astronomers, slowly, across distance, across generations. In the end, Neptune is more terrifying than people think because it is not one simple kind of danger. It is not just cold. It is not just windy. It is not just far away. It is the combination that matters. A planet with no solid surface, wrapped in supersonic winds, sitting more than 30 times farther from the sun than Earth, receiving sunlight so weak that noon feels like twilight, generating storms large enough to swallow our planet, radiating internal heat from hidden depths, carrying a tilted magnetic field, surrounded by faint rings and strange arcs, orbited by a captured moon that erupts geysers at temperatures where nitrogen freezes. That is Neptune. Not a peaceful blue marble, not a calm endpoint, not just the last planet in a school diagram. A real world, vast and active, in the cold outer dark. It teaches us that distance does not mean stillness. It teaches us that cold does not mean death. It teaches us that beauty does not mean safety. It teaches us that even the planets we have known by name since childhood can still be deeply alien when we truly look at them. And maybe that is the most important feeling Neptune gives us. The solar system is not fully domesticated. We have named its planets, mapped their orbits, sent spacecraft to them, and placed them in textbooks. But naming something is not the same as understanding it. Neptune has a name. It has numbers. It has images. But it still holds secrets in its clouds, its storms, its interior, its magnetic field, its rings, and its captured moon. The farther we go from the sun, the more the familiar rules seem to loosen. Light becomes weak, time becomes long, the sky becomes darker, and the planets become less like places we can imagine standing on, and more like deep physical mysteries. Neptune waits there, blue and distant, at the edge of the major planetary system. It does not need to move toward us. It does not need to threaten us. It only has to exist, silently turning in the dark, with winds screaming through its atmosphere and storms forming where the sun is almost too weak to matter. That is why Neptune is more terrifying than you think, because the terror is not that it is a monster. The terror is that it is real. There is another reason Neptune feels strange. It was almost seen before it was understood. Galileo observed Neptune in the early 1600s, but he did not recognize it as a planet. Through his telescope, it appeared like a fixed star, just another faint point of light. That detail is haunting. Neptune was there in the field of view, silently waiting, but human understanding had not yet caught up to what the eye and instrument had recorded. The planet was present, but the concept was missing. That happens often in science. Sometimes the data exists before the meaning does. A mark on a plate, a wobble in an orbit, a faint signal, a tiny difference between prediction and observation. At first, it is just an error, a curiosity, a detail. Later, it becomes a new world. Neptune's discovery belongs to that tradition. It reminds us that the universe does not reveal itself only through dramatic appearances. Sometimes it reveals itself through small inconsistencies. The irregular motion of Uranus was one of those inconsistencies. Astronomers could calculate where Uranus should be, but observations did not perfectly match. The difference was small, but real enough to demand explanation. Either the mathematics was wrong, the observations were wrong, or something unseen was pulling Uranus from beyond? The answer turned out to be a planet. This gives Neptune a ghostly origin in human knowledge. Before it had a face, it had gravity. Before it had a clear image, it had influence. Before it was seen as a disk, it was felt as a mathematical pressure on another world's path. That is a very different discovery story from Mars shining red in the night or Jupiter blazing bright in ancient skies. Neptune was not obvious. It was inferred. It entered human awareness as an unseen cause. That discovery story still affects the way Neptune feels today. It is the planet of hidden influence, the world at the edge that made itself known by disturbing another planet's motion. Even now, when astronomers search for possible distant objects beyond Neptune, they use similar logic. Look for patterns, clustering, orbital behavior, gravitational hints. Whether those searches succeed or fail, Neptune remains the original reminder that unseen worlds can announce themselves indirectly. And that is one of astronomy's most powerful ideas. The universe is full of things we cannot see directly, but can still know through their effects. Dark matter is inferred through gravity. Exoplanets are often detected through tiny dips in starlight or stellar wobbles. Black holes can be found by the motion of stars and hot gas around them. Neptune belongs to this deeper scientific pattern. It is a visible planet now, but it was born into science as an invisible explanation. So when we call Neptune terrifying, part of that fear comes from the way it entered our story, not by shining brightly, not by announcing itself, but by pulling from the dark. A descent probe into Neptune would be one of the most dramatic robotic missions imaginable. Think of the Galileo probe that entered Jupiter's atmosphere in 1995. It plunged into the giant planet, measuring winds, temperature, pressure, and composition until the environment destroyed it. A Neptune atmospheric probe would face a similar kind of fate, but in a colder, more distant, less explored world. It would separate from a carrier spacecraft or orbiter, aim toward the blue atmosphere, and begin its final mission. The probe would not be designed to survive forever. It would be designed to die usefully. At first, it would enter the upper atmosphere at enormous speed. A heat shield would protect it as it slammed into gas, converting motion into heat. Then parachutes might deploy, if conditions allowed, and the probe would begin transmitting data upward to the main spacecraft. It would taste the atmosphere directly. Hydrogen, helium, methane, trace compounds, cloud particles, winds, pressure, temperature. These measurements would be priceless because remote observations can only tell us so much. As the probe descended, the pressure would rise, the light would fade, cloud layers would pass by, perhaps methane ice clouds, perhaps deeper clouds of hydrogen sulfide, ammonia, or water, depending on pressure levels and chemistry. Scientists would finally get a vertical profile of Neptune's atmosphere, not just images of its top. They could test models of how the atmosphere is layered, where clouds form, how winds change with depth, and how heat moves upward from the interior. But the probe's clock would be ticking. Every kilometer downward would make survival harder. The pressure would squeeze. The temperature would change. The signal would weaken. Eventually, the probe would stop transmitting. Maybe electronics would fail. Maybe the structure would crush. Maybe the antenna would no longer communicate through the thickening atmosphere. The last data point would arrive on Earth hours after the probe had already died. There is something profound about that. A machine created by humans, launched from Earth, traveling for years to Neptune, then falling into the atmosphere of a world no human could touch. sending back measurements until the planet destroys it. That is not just engineering. It is a form of exploration that accepts sacrifice. The probe would become part of Neptune. It would vanish into the blue pressure, leaving only data behind. And that data could answer questions we have held for decades. What is the exact abundance of noble gases? How much methane is present at different depths? How does the temperature change below the visible clouds? What powers the winds? How deep do atmospheric patterns extend? How does Neptune compare with Uranus? These are not small questions. They connect to planet formation and the early solar system. A Neptune probe would die quickly, but in that short descent, it could teach us more about ice giants than decades of distant observation. One of Neptune's most underrated terrors is that it may be a preview of worlds we will never visit. Around other stars, planets roughly Neptune-sized are common. Some orbit close to their stars. Some orbit far away. Some may have thick hydrogen atmospheres over deep volatile layers. Some may be mini-Neptunes, smaller than Neptune but still wrapped in gas. Some may be stripped cores, worlds that once had atmospheres and lost them. Others may be ocean-rich planets with deep steam layers and high-pressure ice. When telescopes find these worlds, they often appear only as numbers: radius, mass, orbital period, density, maybe atmospheric hints if the planet passes in front of its star and starlight filters through its atmosphere. But we cannot send probes to them. We cannot watch their storms in close detail. We cannot see their rings or moons. Neptune, by comparison, is nearby. It is in our own solar system. It can be studied directly if we commit the mission. That makes Neptune a Rosetta Stone. If we understand Neptune, we better understand Neptune-like exoplanets. If we understand how its interior holds heat, how its atmosphere circulates, how methane clouds form, how its magnetic field is generated, and how it evolved, we gain tools for interpreting distant worlds. Without that understanding, every exoplanet in the Neptune-size category remains more mysterious. This is why ice giants matter so much. For a long time, public imagination focused on Earth-like planets and Jupiter-like giants. But the galaxy does not only make Earths and Jupiters. It makes a huge variety of planets, many in sizes and compositions not represented by the inner rocky planets. Neptune and Uranus may be our best local examples of a common cosmic theme. Worlds built from rock, ice, gas, pressure, and deep atmospheres, not quite gas giants, not rocky surfaces, but something between. That in-between nature is unsettling. A human can imagine Mars because it has ground. A human can imagine Jupiter as a giant ball of gas because it is so extreme that it becomes abstract. Neptune sits in a stranger category. It is smaller than the gas giants, but still vastly beyond human habitability. It is called an ice giant, but not icy in the simple surface sense. It is blue like Earth, but nothing like Earth. It is familiar enough to name, alien enough to defy intuition. And if the galaxy is full of worlds like that, then Neptune is not an exception. It is a local representative of a vast family of strange planets. That thought expands the fear. Neptune is not just one terrifying planet. It may be one example of a common kind of terror repeated around countless stars in systems we will only ever see as faint signals. Neptune's weather also raises a question that sounds simple but is not. What does a storm mean when there is no surface? On Earth, storms are connected to the surface. Warm ocean water feeds hurricanes. Land can weaken them. Mountains can redirect air. Temperature differences between land and sea shape wind. Even thunderstorms depend on surface heating, moisture, and vertical motion. The surface is not just below the weather, it participates in the weather. On Neptune, there is no solid surface taking part in that familiar way. The atmosphere extends downward, becoming denser and deeper until it merges into the planet's interior. The weather we see is the visible top of a much deeper fluid system. A storm is not sitting above ground. It is embedded in layers of gas and possibly connected to motions far below the cloud tops. This makes the word storm feel almost too small. A dark vortex on Neptune may be the visible expression of deep circulation. Bright companion clouds may form where air rises and methane freezes. Wind bands may shear systems apart. Heat from the interior may help drive convection. Rotation may organize flow into jets. The storm is a surface sign of a three-dimensional atmospheric machine. This means Neptune's visible clouds are like expressions on a face. They show emotion, but not the full mind beneath. When a dark spot appears, we are seeing only the top layer of a process that may extend deep into the atmosphere. When it vanishes, we do not know whether the energy dissipated, sank, changed shape, or became invisible to our instruments. The planet's true weather may be far more complex than the patterns we can see from Earth. This is why long-term observation matters. A single image captures a moment. A year of images reveals change. Decades of images reveal cycles. An orbiter could reveal the vertical and horizontal structure of storms, tracking cloud heights, thermal patterns, winds, and chemistry. Without that, Neptune's weather remains partly like watching shadows on a wall and trying to infer the machinery casting them. The storms are terrifying because they are not simply big. They are signs of depth. They are visible hints of a planet whose atmosphere may be moving in ways we cannot yet map. There is a loneliness to Neptune that no inner planet has. Mars is lonely in a romantic way, a cold desert next door, still close enough that humans imagine footprints there. Venus is hidden, but close. Jupiter and Saturn are distant, but they feel populated by famous moons and spacecraft stories. Neptune's loneliness is different. It is the loneliness of the last major planet, the one beyond which the solar system becomes less familiar and more diffuse. If you were near Neptune, Earth would not be a visible world in any ordinary sense. It would be lost near the sun, a tiny planet drowned in glare from billions of miles away. Every human being who has ever lived would be somewhere in that direction, on a world too small to see. The moon, Mars, Venus, the oceans, the mountains, the cities, every voice and every memory, all reduced to an invisible point in the inner solar system. That perspective is emotionally powerful. Space distances are not just numbers, they are separations. At Neptune, Earth is no longer the central stage. It is a distant birthplace. The sun is still bright, but small. The familiar planets are hidden in the inner glare. The outer darkness surrounds you. The next major landmarks are not warm worlds, but icy bodies, dwarf planets, and the long fade toward interstellar space. This is why Neptune feels like a border. It is not the end of the solar system, not technically. The Kuiper belt extends beyond it, and the Oort cloud may reach vastly farther. The sun's gravity extends into interstellar distances. But psychologically, Neptune is the last great planet. It is the final giant marker before the architecture changes. Borders are often frightening because they separate the known from the unknown. Neptune is exactly that kind of border. It belongs to the known planets, yet it points beyond them. It is visible to telescopes, but not to naked eyes. It has been visited, but only once. It is familiar by name, but unfamiliar in detail. It is both inside and outside our sense of home. That liminal quality may be its deepest fear. Neptune stands at the edge of comfort and says, "Beyond here, the solar system becomes stranger." Even Neptune's name adds to the feeling. Neptune was named after the Roman god of the sea. On Earth, the sea is deep, blue, powerful, beautiful, and dangerous. It hides landscapes below the surface. It contains currents, storms, darkness, pressure, and life. The name fits the planet visually because Neptune is blue, but it also fits symbolically because Neptune is a kind of cosmic ocean world in the imagination. Not an ocean of liquid water on the surface, but an abyss of atmosphere and pressure. The sea metaphor is useful, but only if we remember how alien the planet really is. Earth's ocean has a surface you can float on. It has water, waves, sunlight near the top, and life. Neptune has no such surface. Its blue is atmospheric, not a visible global sea. Its depths are not oceans in the human sense, but layers of gas and high-pressure fluid. Still, the emotional connection remains. Blue depth, hidden forces, pressure increasing downward, storms above, darkness below. Ancient sailors feared the sea not because it was always violent, but because it was vast and indifferent. A calm ocean could become lethal. A horizon could hide storms. Depth could swallow ships without leaving a trace. Neptune carries that same emotional structure into space. It looks calm from far away, but its calmness is not safety. It is distance. The Roman Neptune ruled waters, storms, and the unknown beneath the surface. The planet Neptune, by coincidence and poetry, rules a similar feeling in the solar system. It is the blue deep at the end of the planetary realm. A world whose visible surface is not a surface at all. A place where falling means sinking into pressure rather than landing on ground. The name may be mythological, but the fear is scientific. Neptune is the sea god turned into physics. From Earth, observing Neptune is an exercise in humility. Even in a telescope, Neptune is small. Not small in reality, of course, but small in the sky. It is a giant planet nearly 4 times wider than Earth, yet distance compresses it into a tiny disk. A backyard telescope can show it as a bluish dot, but not as a world full of storms. To see details, astronomers need major observatories, adaptive optics, space telescopes, careful processing, and patience. That changes the kind of relationship we have with Neptune. Mars invites direct attention because surface markings, polar caps, and changing features can be seen from Earth under good conditions. Jupiter reveals bands and moons even through modest telescopes. Saturn shows rings. Neptune gives almost nothing easily. It forces science to work harder. The planet hides behind faintness, distance, and angular size. It does not reward casual looking with obvious drama. But in different wavelengths, Neptune becomes more revealing. Infrared observations can show heat patterns and high clouds. Methane absorption bands can help scientists separate cloud heights. Bright storms can stand out against darker atmospheric layers. Hubble and large ground-based telescopes can track changes over years, giving us a slow-motion view of a weather system billions of miles away. Each wavelength is like a different key for the same locked door. This is one of the reasons astronomy is so powerful. Human eyes see only a narrow slice of reality. Neptune in visible light is a blue disk. Neptune in infrared, ultraviolet, and radio-linked measurements becomes a physical system. Temperature, composition, winds, clouds, magnetism, and internal heat. The planet does not change, but our method of seeing changes. And every method reveals a different version of the truth. That is why Neptune remains scientifically alive, even without another spacecraft. We are still watching it. We are still seeing storms appear. We are still refining its color. We are still measuring its atmosphere. But remote observation has limits. At some point, the only way to truly understand a world is to go there again. Until then, Neptune remains a distant signal, a few pixels carrying an entire planet. There is also a dangerous misconception hidden in the phrase ice giant. The word ice can make Neptune sound frozen, solid, maybe even less violent than the gas giants. But in planetary science, ice giant does not mean a giant ball of ice you could walk across. It means a planet rich in volatile compounds that were icy during formation. It is a compositional category, not a promise of a frozen surface. This matters because language shapes imagination. A person hearing gas giant understands there may be no surface, but ice giant can sound more solid. It can make people imagine a giant frozen planet, perhaps with a crust or shell. Neptune is not that. Its visible layers are atmosphere. Its deeper layers are likely hot, dense fluids under enormous pressure. The materials called ices are transformed by the planet's mass into something far removed from snow, glaciers, or frozen lakes. The same problem happens with words like ocean. Scientists may talk about a superhot water layer or deep fluid mantle inside Neptune. But this does not mean there is an ocean under clouds in the way Europa may have an ocean under ice, or Earth has oceans under sky. The pressure is extreme, the temperature is high, the chemistry is mixed, the state of matter may be exotic. It is not a place for submarines, waves, or life as we know it. Neptune teaches us that familiar words can become strange in space. Ice is not always cold. Ocean is not always surface water. Weather is not always above land. A blue planet is not always Earth-like. This is one of the deepest challenges in understanding the solar system. We borrow words from Earth because Earth is our only everyday reference. But beyond Earth, those words begin to stretch. Eventually, they almost break. Neptune lives in that broken language region, where we need familiar terms to begin the explanation, but must abandon familiar images to understand the truth. That is another kind of terror, the terror of concepts failing. The planet does not just threaten bodies, it threatens assumptions. If Neptune were closer to the Sun, it might be famous for completely different reasons. Imagine Neptune at Jupiter's distance. Its storms would be easier to observe. Its moons and rings would be more accessible. Spacecraft could reach it more often. Its blue atmosphere would be one of the great sights of the night sky. It might be a centerpiece of public imagination, a planet everyone knew not just as the last one, but as one of the most dynamic worlds in the solar system. But distance changes reputation. Because Neptune is so far away, it becomes simplified. It becomes the blue one, the far one, the cold one, the last one. Its complexity is hidden not because it lacks drama, but because the drama is hard to see. This is an important lesson beyond astronomy. Things do not become less interesting because they are far away. They become easier to ignore. Neptune is a victim of its own remoteness. Not scientifically, because planetary scientists understand its importance, but culturally. The public often overlooks it because the strongest images and stories belong to planets with more missions and more familiar visuals. Mars has rovers. Jupiter has giant storms and famous moons. Saturn has rings and Cassini. Pluto had the emotional drama of New Horizons. Neptune had Voyager 2, and then decades of waiting. That waiting has made the planet feel quieter than it is. But the quiet is not Neptune's. It is ours. The planet has been storming the entire time. Its winds have been racing. Its internal heat has been leaking. Triton has been moving in its backward orbit. The rings have been circling. The magnetosphere has been wobbling. Neptune did not become less active because we looked away. That may be the final reason it feels terrifying. A world does not need our attention to remain powerful. So as this journey ends, imagine Neptune one last time, not as a simple blue circle in a school diagram. Imagine it as it really is, a distant ice giant turning slowly in the weakened light of the sun, wrapped in winds faster than anything on Earth, carrying storms that can appear and vanish like dark wounds in its atmosphere, hiding a hot, pressurized interior under cold clouds, surrounded by faint rings, strange arcs, small moons, and Triton, the captured frozen world that still erupts into space. It is beautiful, it is remote, it is real, and somewhere out there, more than 30 times farther from the sun than Earth, Neptune continues to move through its long orbit, taking 165 years to complete a single journey around our star. Most of us will never see it through a telescope with our own eyes. No human has ever been there. Only one spacecraft has ever passed it closely. And yet it remains one of the most important worlds in our solar system, a reminder that the familiar planets still contain mysteries deep enough to challenge us for generations. Neptune is not terrifying because it is coming for us. It is terrifying because it shows us how alien our own solar system can be. It shows us a world where the sun is weak, where there is no ground, where storms become planetary, where cold does not mean stillness, and where beauty can hide violence on a scale we can barely imagine. And if we ever return to Neptune, if one day a spacecraft enters orbit and begins to watch it closely, the planet will almost certainly surprise us again,